welcome back to Sustainably U Podcast. This is me, Simi, and as usual, my partner in crime, we have Philip.
Hello.
And Vibha is out for a yoga retreat and should be back in for the next episode, hopefully. Continuing with our topic of sustainable energy. So in the last episode, we covered petroleum, we covered geothermal energy, solar, and continuing on. Today, in this episode, we'll start with the difference between energy and power. So it's something that most people really confused about. We always use the term for the same. We use power for energy and energy for power. However, it's two different terms. Mm-hmm. So Philip, what is the difference between energy and power?
Well, energy is, as we talked about in the last episode, it's the property that helps a thing move or produces motion or the ability to do work. Power is how fast can you do that work or how fast can you withdraw that energy. So let me give you an example. So if energy can be compared to money, and so let's say if you have 100,000 joules of energy in a battery, and if you have $100,000 in your bank, and let's say we can compare them. So power would be how fast can you withdraw that energy from the battery. So if you can withdraw 100,000 joules in a second, that power would be 100,000 watts. So power is energy over time, and it tells you how fast you can withdraw or charge energy. And so in the money case, it's how fast can you withdraw $100,000? Is it at $10 per hour or $1,000 per day? Mm-hmm. You know how banks put limits on your account. Similarly, a battery will have a limit on how fast energy can move in or out. Similarly, an engine will have a limit on how much energy it can take or supply per second. And so the higher the power, the larger the device tends to be. So bigger batteries can supply more power, that is more energy in a given second, and so on.
So talking about energy and power, I mean, that was a great example to understand the difference of energy and power.
Well, let me also mention the units that we use. So for energy, the common units is joules. And
a joule is the amount of energy required to lift an object of 1 kilogram to a height of 10 centimeters approximately.
So joules is a very commonly used unit. Another one is calorie. We use calorie for chemical energy or food energy. But you have to be careful with calorie because Americans like to say calorie, but when they're really meaning kilocalorie. So on a packet of food, say a McDonald's burger, you might see 300 calories written on it in the US. But if you go across the border to Canada or to Europe or to anywhere else in the world, you'll see 300 kilocalories written on the container for the same burger. So just know the difference.
So I think you probably need to tell them what is kilo. So what does 300 kilocalorie mean?
So a calorie is equal to 4.2 joules. In other words, it's the amount of energy required to move an object of 4.2 kilograms to a height of approximately 10 centimeters, or a 1 kilogram object lifted to a height of 42 centimeters approximately.
But a burger will have 300,000 of those calories, not just 300 calories. Yeah. And so that explains why after you eat a cupcake, you might want to work out for several hours to work out that cupcake, because it's actually thousands of calories, kilocalories. Now, a couple more units we commonly use is barrels of oil is used as a standard unit of measuring energy. So that would be the amount of energy present in 1 barrel of oil. Another energy unit is the kilowatt hour. Now, the word watt, which is the name of James Watts, it's used as a unit of power. So you have a horsepower. So 1 horsepower is 746 watts. But when you're paying your electricity bill, you pay for the energy, which is the power times all the time. Power multiplied by the time that you've been using the power over. So it'll be measured in thousands of watt hours or kilowatt hours. And that is energy. So kilowatt hour is energy. Watt or kilowatts is power.
So let's start with wind power or wind energy, which is mostly the use of wind turbines to generate electricity. So we've been recently hearing a lot about wind farms. What is it exactly?
Well, you're probably getting the picture of a 3-bladed wind turbine on a tower that could be about, say, 50 meters tall. That's about 150 feet tall. So that's the picture you may have in your mind's eye that you might have seen as you were driving by them. So those are horizontal axis wind turbines because the axis that it turns on is horizontal and you can look into them as opposed to your ceiling fan, which is a vertical axis. The most common types of turbines are the horizontal axis wind turbines, the 3-bladed ones. And they range in power from hundreds of kilowatts to about 10 megawatts in size for the larger bladed ones. And the largest ones at about 500 feet high are rated at about 17 megawatts. Mm-hmm. And a wind farm would have hundreds of these wind turbines. Now, the wind farms are located in what's called wind corridors. And these are places where the wind is relatively constantly blowing at
like
good
seashores?
Speeds. Yes, along the shores. It could be close to mountains where there are wind corridors created by the mountains that tends to concentrate the wind and speed them up. So the wind corridors are located usually far away from cities, and that means that you would need a grid to bring the power to the cities. Now, the wind speed has to be higher than about 7 kilometers an hour, which is about 4 miles an hour, up to about 100 kilometers an hour, which is about 60 miles an hour. So the turbines can operate within that speed range. If it's below that, the turbines will not turn, and if it's above that, it's too dangerous, and it would destroy the turbines, and so you would have to brake them, as in apply brakes to stop them from turning.
So we do know that wind farms are much cheaper than the coal and gas plants or the fossil fuel. How is it in comparison to putting up solar structures, to derive solar energy?
Yeah, so wind farms appear cheaper and cleaner on the surface, but we can look behind the scenes and to see if they're really clean. But what you are asking refers to what is called the levelized cost of energy. Mm-hmm. And so that's a comparison on a common scale of the various types of energy sources. So when you look at your electricity bill, you see the units as kilowatt hours. And so the average electricity rate that people pay, say in the U.S., is at about 15 cents, U.S. cents per kilowatt hour. And that could be for typical fossil fuels-based utility supply. Wind is quite cheap at about 3 to 4 cents, U.S. cents per kilowatt hour. And solar is down less than that at about 1 to 2 cents for a utility solar farm scale solar power source based on solar PV. Natural gas is the next more expensive one at about 6 cents per kilowatt hour. And then geothermal at about 7. And coal is slightly above 10 cents per kilowatt hour.
Okay, so relatively, it's quite a reasonably priced source of energy.
Mm-hmm. Yes, it is quite cheap when you compare it to traditional energy sources like coal and thermal and also nuclear, which are all in the 10 to 15 cents per kilowatt hour range, and wind being about 4 to 5 cents per kilowatt hour.
That sounds quite good and quite reasonable in comparison to the other energy sources that we are currently using.
Yeah.
How about, let's talk more about the sustainability part of wind farming. How about the raw material? So historically, like in old days, the wind power, they used to use wind power from windmills and wind pumps, which was built from bricks or stones and
wood.
Metal, wood, which was very, very sustainable. But today, what is it made of? Is the raw material, where is it coming? First, obviously, is where are the raw materials coming from? Are they made within the country? Secondly, what is the material? Is it recyclable?
So most people remember the story of Don Quixote, which is from the early 1600s. And those windmills were made of wood and would be about 2 stories or 3-story high. But their power rating would be quite low, maybe about 1 kilowatt to 5 kilowatts in power, compared to what we have today, which is about 10 megawatts, typically in the range of 1 to 15 megawatts in size.
But also in comparison to old days, I mean, we use energy not energy, to rephrase it, electricity for absolutely everything. So the amount of need we have is also way, way high.
Right. So now wind turbines are used exclusively for electricity generation. So let's look at the manufacturing. The wind turbine blades are made of plastic or composite fiber. And so that would have to come from a petroleum source or a coal source, which is not really sustainable. And then there are many components inside, such as the generator and then the wires, the cables, all of which come from different countries. And they may be assembled in place. In Northern Europe, they do manufacture these wind turbines, but again, the parts come from different parts of the world. And then they have to be moved to the site, and a concrete base has to be built if it's on land. If it's in the water, you have to build a rig and a platform made of metal. And then the tower and the turbines have to be assembled in place, all of which takes energy, usually from fossil fuel vehicles and cranes.
So there's a carbon footprint to it.
Exactly. Oh, and there's one more thing most people are not aware of. Inside of the wind turbines, there is a lubricant, which is a petroleum-based oil. And there are tons of it in these large wind turbines. And that is flammable as well. And so if wind turbines get hit by lightning, they can catch on fire and burn down.
So to create a wind turbine, to generate electricity which is lower in CO2 emissions, there's a huge carbon footprint.
Exactly.
We still need petroleum or natural gas.
Yes.
Now, one more thing about wind turbines. While the stem of it, what do you call
the tower?
The tower itself is stainless steel. The blades are made of lightweight plastic composite materials. Now, which needs to be, obviously, the reason why it is because it needs to be lightweighted. But the problem is it's huge. And it's impossible to recycle.
Yes.
You cannot recycle it.
So the typical lifetime of a wind turbine is about 20 to 25 years.
Yeah.
But a lot of them do not last that long. They break down earlier because of natural reasons. But once they are decommissioned, then presently I have seen many companies burying the wind turbine blades, such as burying them in the soil.
Which is useless because it will come up.
So that's not a very positive thing. But there is a solution to that. Because it's plastic, which is a hydrocarbon, we can actually turn that hydrocarbon into syngas and hydrogen using plasma gasification. So wind turbines can be crushed down and then fed into plasma gasifiers. And then they can be turned into syngas, from which hydrogen can be liberated, or the syngas can be used to produce fresh plastics or new liquid fuels. So this is a very new and positive development, but I haven't seen that being applied for wind turbines yet.
No.
But this is a very good possible solution.
That's definitely has to be that solution when so many more companies are looking towards installation of wind turbines. I don't know, regardless or without understanding. I'm not sure about that term because they very much should be aware of the amount of waste they are creating that will eventually go into landfill any which ways and stays there for the longest time possible after our lifetime.
Yeah.
So plasma gasification seems to be the answer to
Yes.
all our problems. I wonder where the loophole is.
Well, I'm sure, there are negatives, but right now it's a really good technology with lots of benefits.
So talking about waste, biogas has been there for a long, long time. This has been there before we started solar, not before wind, but yeah, or maybe even before wind, because we were always reusing waste as human beings. Biogas, what is biogas?
So biogas is mostly methane, but it'll have other components such as sulfur oxides and hydrogen sulfide.
So when you say methane, where does that come from? As a layman, what can you say where it comes from?
So methane is produced by the
cow? That's what I remember, because when you say biogas, my first memory is in my grandparents' house. It's an old ancestral farmhouse, and my grandparents had tons of livestock, cow, goat, and obviously they all poop and do all sort of things. Everything.
Flatulence.
All sort of excretion that comes out of the goats, cattle, whatever. It used to go into this big tank. Any sort of waste goes in there. It's covered. And it used to light up the house. That was a source of gas for fire. Cooking.
Okay.
Yes, cooking gas. That's my first memory of biogas.
Well, without dating yourself, how long ago was that?
This was... No, that would reveal my age. I'm not going to say that.
Never mind. So, yeah, we can see that biogas has been in use as a fuel for a long time. Not that long. Simi is quite young. But
younger than you.
So biogas is produced by the digestion of biomaterial by bacteria and also our digestive enzymes. And it's a mixture of many gases.
I have to. I'm going since you said about a lot of bacteria in our gut, I just wanted to give one of the sources of methane.
Yeah, is flatulence. Yes.
You just use words which is like sounds so good, right? You mean like fart?
That's a colloquial term for it. Yes.
Yeah. Now don't try to go and put your bum on fire, though.
Well, we've seen that in what's that movie by Jim Carrey?
My son had tried.
Okay. Yeah.
Tried something. He
don't do this at home.
No, he wanted to do that.
But again, that's an example of harvesting biogas for energy. So biogas can be produced from almost any biomaterial if you find the right bacteria. Most of the common bacteria will digest in our foods and food waste, but also even leaves, grass cuttings, and waste wood, and so on.
So you're saying anything that is alive?
Yes.
Plants,
biological material.
Biological material, whatever comes out of your body, the plants, trees, leaves that fall, animals excreting, and whatever, that can all be put in one place and this fuel can be created.
Yeah, the gaseous fuel.
Okay, but in comparison to other energy sources that we spoke about, how much are we using this? Is it currently very prevalent, especially when we talk about animal farming and we say that it's not very sustainable because of the amount of pollution it creates? The cattle farms and stuff. Is bioenergy currently being tapped into? Is it as sustainable source of energy?
Well, it could be part of a sustainable mix of energy. So right now, there's very little of it being utilized for energy, for, say, electricity generation, or for, say, transportation purposes, or the most common form, which is for cooking. So accounting for all of that, it would still be below 1% of 1% of the world's energy consumption. So very little bioenergy is being used. Biogas energy is being used.
So in my mind, what I'm thinking is, especially if there are people in the farming industry, for them, this is quite a good place to go to get energy, to use what's a waste right now, to put it back into use.
So this could be part of the sustainable mix.
But it cannot be a sole.
No.
Yeah.
You cannot be off the grid using biogas. But it can be scaled up if you have a steady supply of biomaterial, such as, say, animal waste. You don't want to use human waste because, the main problem is psychological. People have an aversion to human waste being used for energy. But there's plenty of sources of animal waste from farms who would find it profitable to generate biogas for their own consumption.
So it could be part of a energy mix, especially if you are part of the agriculture sector. Great way to utilize the waste and use it to reduce your energy bills.
So the problem is it takes too long to generate the biogas. It takes several days to get a good flow rate.
So it's not constant.
It's not. And so it has to be, even though you're generating waste and you can add more waste to the reactor, it takes a long time to produce the biogas. And second is that the facility itself needs constant maintenance because you have to remove the solid residues and replenish it with new biomaterial. So as a single source of energy, it's not feasible at all.
No.
I've seen a lot of people in rural areas having small biodigesters for the kitchen waste.
Like we said, it's a great part of the mix. The same as small solar panels on your rooftops. This can be a great part of the mix for people in agriculture sector.
Yes.
To put it in.
So waste can actually be considered an alternate form of energy along with petroleum and coal and hydro and so on.
Philip, we'll save the best for last, where we talk about bioenergy from waste.
Yes.
Yes. That's your forte, and I'll give you that.
Yeah. Okay. So it's not just bioenergy, but it's energy from biomaterials.
Yes. So, of course, bioenergy, as we said, is also a great part of the mix, but it cannot be a complete reliable source for energy. However, in recent times, one of the things that's making a lot of noise has been hydrogen energy. To me, it's been a bit complicated to understand. Obviously, I took an hour or two of yours today to understand hydrogen energy. So in simple layman's language, what is hydrogen energy? How is it created?
So hydrogen, when it reacts with oxygen, produces water and releases energy in the form of heat. So the most common way of harvesting hydrogen chemical energy is by combusting it in an engine or a turbine. There aren't any large-scale turbines that can operate on hydrogen alone. So presently, because hydrogen is not a very safe fuel, hydrogen can be blended with other gases in a turbine or an internal combustion engine. Another way of harvesting hydrogen energy is in a fuel cell where the oxidation reaction, that is hydrogen plus oxygen reaction, is done in a more slower manner, not by releasing heat, but by producing electricity. And that is a direct step from chemical energy directly to electricity without having to go through burning or motion capture, using a generator or something. You can go directly to electricity, and then that electricity can be used for whatever purpose you want, such as turning a motor in an electric car, or for running electric appliances and so on, such as on the space station out in space. So hydrogen, oxygen fuel cells are used on many satellites as well as space stations.
So 2 questions there. Hydrogen energy, is it renewable? Second, obviously we've been listening to hydrogen energy a lot because of the sustainability factor in it, that it's sustainable and it's net zero carbon emission. So maybe we can start with renewable. Is hydrogen energy renewable?
Yeah, I have to give a yes and no answer because it depends on where the hydrogen comes from. Now, obviously, everything has hydrogen, hydrocarbons, carbohydrates, water. So hydrogen is the most common element in the universe, but it's always combined with something else. And so you have to liberate that hydrogen. And that takes energy and money and work to liberate that hydrogen. So depending on those factors, it could be renewable or it could not be. If the hydrogen is coming from petroleum or natural gas or a fossil fuel such as coal, then obviously it is not renewable. But if it came from water through electrolysis, it is definitely renewable.
So we like to settle with the renewable because since hydrogen is available, it's just about tapping into the technology to release the hydrogen. It is. Do you agree with that? Since you just shake your head, I'm not sure.
Yeah, again, if it's a fossil fuel, then which is not renewable, then we can say once it's used up, it's gone. So if it's coming from water or waste, then it can be renewable.
Perfect. Coming to the second part of it, about it being a sustainable source of energy. One of the things that we spoke about was how expensive it is, and also the storage part and the danger. So is it very expensive, the whole combustion, regardless what the source of the raw material is? How expensive or how not expensive is it to derive hydrogen?
So that brings up an interesting point about hydrogen, and they give it colors. So they color code hydrogen by how it is produced.
Oh, okay.
So, for example,
does that affect the cost?
It does.
Okay. So you can go into the marketplace, or wherever, and then you can say, okay, I like this hydrogen, a blue or a Coke hydrogen, and then that has a different price to, let's say, Pepsi hydrogen.
Well,
I don't know.
Yeah. So the color codings are green, blue, gray, black, brown, pink, etc. But hydrogen gas is colorless, right? So it has no color inside the container. So on the container, you might find a label with a color coding. So green hydrogen is produced from renewable energy source by electrolytically breaking water into hydrogen and oxygen. So you can use solar or wind energy to electrolyze water to produce hydrogen, and that would be green hydrogen. Blue hydrogen is produced from natural gas using steam reformation.
So when you say natural gas, it's what petroleum is derived from too, right?
Yes, it comes from under the ground, and then
Fossil fuel.
And you treat it with high pressure, high temperature steam and cause them to react in a reactor, and you get hydrogen as well as oxygen and other products. That hydrogen can then be stored, and it would be classified as blue hydrogen. There are other colors as well, but those are the two main color codes.
So the blue hydrogen can be, I'm not going to go extensively into it, but it can be, obviously it's non-renewable, but it's also a way of using up the waste when you are digging out biogas. Fossil fuel.
Yes. So natural gas is associated with petroleum deposits, and you might see petroleum companies flaring natural gas because it's cheaper to just burn them away than to capture it. And so that natural gas could be captured and actually used for hydrogen production.
So that was part of it, but it being sustainable. The second part of it was storage. That's also part of the sustainability of any sort of energy source. How well can one store the hydrogen?
So it's very difficult. If you've seen the space shuttle launch or a photo of the space shuttle, there are those huge tanks that they carry hydrogen and oxygen. And you might see them smoking. And the reason is that hydrogen and oxygen is contained in those tanks at extremely high pressures and at extremely low temperatures. And they call it cryogenics because for the technology that compresses hydrogen and turns it into liquid for storage. And we're talking about minus 250 degrees centigrade or
minus 420 degrees Fahrenheit,
which is extremely low temperature. So to store hydrogen efficiently in a small space, small container, would take cryogenic technologies. But so that rules out transportation then, like a car.
Oh, I thought hydrogen was the big it thing for transportation.
Yeah, so
that's what I thought.
So you need then, without cryogenics, you just have very high pressure hydrogen.
And very dangerous.
So that can make it dangerous. Okay, if the tank ruptures, hydrogen might go upwards because, like hydrogen balloons, right? The hydrogen wants to go up in our atmosphere. So in one sense, if there's a leakage in your hydrogen car tank, hydrogen will vent and escape upwards, which can be inherently safe. But there can be explosions that can happen. So there's a huge safety factor that has to be
so currently, what are we using hydrogen for? Can it be part of the energy mix that we were talking about in terms of deriving electricity, or is it in smaller battery kind of things that you can use it for?
So hydrogen will eventually be used for fuel cell cars once these safety and storage issues are worked out, and fuel cells become cheaper and have better longevity, because right now fuel cells have very short lives.
Yeah.
But the main usage for hydrogen presently is for, or in the future that's being determined, hydrogen will be used for electricity generation using, gas turbines, which have not been built yet, because hydrogen has a tendency to explode or detonate. And so new gas turbines have to be created that would handle hydrogen. And then hydrogen would be transported through pipelines, like natural gas is done now. And it can be transported from, say, North Africa, where there's plenty of sun. And then the sun can be harnessed to electrolyze water. And then the hydrogen generated can be transported through pipelines under the Mediterranean Sea into Europe. So that's one of the main uses being perceived for hydrogen. But there are many other uses, such as in industry for producing steel, can be used for producing cement rather than fossil fuels. It can be used for manufacturing of a wide variety of things, including one practice that we should stop doing, which is hydrogenation of vegetable oils. That's something we should stop doing. So hydrogen has lots of uses. Another use for hydrogen is for producing ammonia. Ammonia molecule is one atom of nitrogen with 3 atoms of hydrogen. And ammonia is also used as a fuel as well as for industrial purposes. So one of the big uses for hydrogen presently is to produce ammonia.
From our little talk today, I feel hydrogen would probably end up being part of the mix, part of the basket. It will be used in some industries. It would probably be used in transportation majorly, but it won't take over petroleum. Like the current giant is petroleum. We
Right.
use petroleum for everything. So hydrogen is likely not to be taken so seriously.
No,
or,
it is.
It's not going to be taking over.
Yeah,
that
not
big.
in the next 20 years. I don't see all these issues being resolved for transportation within the next 20 years.
Oh, okay.
Yeah.
So, what do you think can take over the giant fossil fuel? Why I call it a giant is also because for everything we use fossil fuel, and that's why it becomes then very difficult to get out of. So one of the things I believe can take over is nuclear. So when we talk about nuclear, most of the time we are all talking about world wars and thinking about wars, and that's why countries have nuclear reactors, etc. Maybe you should bust the myth that why is countries interested in having nuclear plants?
The word nuclear brings fear and revulsion in many people's minds, but nuclear has been around for quite a while. But most people have images of mushroom clouds in their minds when they hear nuclear.
And dead people.
And for obvious reasons. And those reasons are why nuclear is so tightly regulated and controlled. You cannot have your own nuclear station in your basement because of that.
I hope nobody's trying that.
There was a high schooler who built a nuclear reactor
No way.
in the US, and I think he was stopped and his nuclear reactor was taken away.
And was he admitted into NASA?
I'm sure he has a good job now.
He seems to be quite a brainy guy, but using it for the wrong...
he was experimenting, which is a great thing to do. So go for it.
Before he explodes his parents' basement and everything else.
Yeah. So there are two kinds of nuclear. There's fusion reactors, and then there's fission reactors. So fusion is where elements are fused to create larger elements, and fission is where larger elements are broken down into smaller elements.
That's actually that I found it. I never thought it's only because it's fission, because dividing something in my mind, and I think in most people's mind, do not create energy. You're removing something, but colliding something, obviously for obvious reasons, create energy.
Yeah.
So maybe I would like to hear about fission first, because it's how do you removing separation create energy?
So fission is where a larger atom, a radioactive atom or fissile atoms, such as uranium-235, is broken into smaller atoms. And in that process, a large amount of heat is released. And the heat released is based on the famous Einstein's formula, E equals mc square, where m is the mass difference between the larger parent atom and then the daughter atoms. So there'll be a tiny mass difference. And that mass difference times the square of the speed of light is the energy released for every atom that's broken. So we're talking about millions of these atoms, billions.
Can you give a contextual example?
Yes.
So it's more easy to understand for people.
Okay, to give a very quick comparison, if you burn 1 kilogram of gasoline or petrol, you get about 45 million joules. And if you burn 1 kilogram of hydrogen, you get 120 million joules. But if you have 1 kilogram of uranium-235, you get 79 million joules.
Whoa.
That's 79 million joules.
Wow. That's a resource we need to tap into.
Yes. Now, uranium is just one fissile material. There's so many others. Well,
quickly, if you can say, what's a fissile material?
Something that can break into smaller materials, smaller elements is called a fissile material.
So currently for nuclear fission, we are using only uranium?
Well, the most common use, because of the type of reactors that are being used around the world, uranium-235 is the main fuel type that's being used.
Is it a renewable?
No, it's
material?
Not renewable, as in it gets used up. But that's not a bad news, because there's plenty of uranium, and most of the uranium comes from under the ground. It's mined from uranium mines. But actually, there's a radioactive material all around us in the soil, and it's present in very tiny quantities, but all around us. So we're talking about 1 part per billion. So if you take 1 kilogram of soil from the ground, 1 billionth of that 1 kilogram would be uranium. And another thing that's in there is thorium. So uranium and thorium are present in very tiny, but 1 to 4 parts per billion all around us, and also in the oceans. And we do not have very good technologies to retrieve this, but it's just a matter of time, given human ingenuity and the way technology is progressing.
Given that it's non-renewable, one good news is you use such small amounts of uranium for fission or fusion in the nuclear reactor that it will not probably be as exploited as you might do with other non-renewable resource. But having said that, since it's a non-renewable resource, doesn't it run the risk of exploitation? Because uranium is highly valuable, it can easily create black markets and exploitation and all that stuff that we do have with many other materials. That's
why uranium is so tightly controlled. I mean, at every country level, and as well as from the UN, and every bit of uranium is accounted for and traced and highly regulated. So because of those safety and political issues. Now, that's true that we would continually use up uranium, but there are ways to produce new uranium from other elements by transmutation. And also, thorium has not even been utilized yet. I mean, we just have experimental thorium reactors, maybe 1 or 2 thorium-based reactors in China and India yet. So thorium is much more plenteous than uranium, and we have not started using it.
So when we say these elements are non-renewable, even if it's, let's say, plentiful for right now, but it doesn't renew on its own. If we use it up, it's used up. Then how is it part of the sustainable energy?
Well, it produces very little carbon footprint, and it's non-polluting, and it runs for a very long time. That is, these nuclear reactors. The present generation is generation 3. So just the one that was installed in the United Arab Emirates is a generation 3 reactor, which are safe and can run for about 60 years and even longer if they're maintained well. So there's nothing else that can match those numbers in terms of, CO2 production, longevity, reliability, and efficiency.
I mean, reliability, I don't know. It's a reactor at the end of the day. And then there's places where it's high calamity prone and war prone areas and things like that. You cannot think of having. So it is not across countries. Everyone can have a nuclear reactor because it can be misused and it needs high security and all that stuff. It's not like having a petroleum plant, which can just.
So uranium can produce plutonium or other material that can be used for nuclear weapons. So that's one drawback for uranium. And that's why it has to be highly regulated and protected.
But can that be changed in the future?
Yes. So we can have SMRs, small modular reactors, where the fuel is contained in such a way that it cannot be then harvested for weapons making. And also, plants are protected with safety and security. Just like, other things that we have in our lives, like diamonds and money, the money printers, there's a lot of security around it. And also government officials, they get a lot of security and protection that regular people don't. So I don't see security as a showstopper for for nuclear energy.
But you could see it taking over other energy sources.
Yes. So if you want to cut down on CO2 production and if you want to clean your environment, I don't see another option presently than nuclear fission reactors. And we will get into fusion in a bit, but nuclear fission is the most effective source of clean energy that is available at the moment. And if you want to have an alternative to petroleum-based transportation, then you need electric cars. And to power and charge all those electric cars, you need a lot of energy, much more electricity than the current production capacity of the world. You need to triple that or more. And so that electricity has to come from somewhere that is clean, and nuclear is the best source.
That topic about electrical cars and the energy it needs, it deserves episode on its own in the first season. So we will be covering it for all of you guys interested in
electric vehicles
or fast new transportation, etc. Okay, so moving on to fusion. So what's different? So you explained fusion is when you collide two atoms and the energy release.
Well, when you fuse them, when you join, say, two hydrogen atoms to form helium, then there is, again, a tiny mass difference. And that mass difference times, the E equals mc squared formula gives you a humongous amount of energy release in the form of heat. Now, fusion has always been promised as being 50 years away. So 50 years ago, fusion was 50 years away. And today, fusion is still 50 years away.
Is it?
Yeah, so it's this fairy tale sounding thing that's always been promised to be in the future. There is a lot of development in the fusion arena. Now, I'm going to get into some controversy here in a short order. But fusion, if it happens, and I believe it will happen because I'm very optimistic about human ingenuity and progress. So when it does happen, it will be the only source that we will need for energy, because we will have endless energy that is clean, non-polluting. It doesn't produce any CO2 or any other gases that can hurt the environment. And we'll have clean energy available for everyone. So that's the future. So if we believe that fusion is going to be available, let's say in about 40 to 50 years, then what that would mean is we can rethink about our plans for the future for other energy sources. We just have to wait it out for about 50 years. So we don't have to worry about petroleum running out or, petroleum affecting the climate change and so on.
But you just said that was the plan 50 years ago.
Yeah. So that is a problem. So is fusion going to happen? Because if it does happen, it would solve all of our present problems, right? Now, there is some news on the horizon. There's lots of research happening in the US and in Europe. And China also is getting on board with fusion research. That is experimental fusion research. There's a lot of theoretical research and computational research happening around the world, but experimental facilities are located in the US, one at MIT, and in Europe, and then one in France, and then in China. Now, here's the controversial part. Now, I think that they are going for the most difficult form of fusion, which is they're fusing hydrogen, that is heavy hydrogen, deuterium and tritium, into helium. And this is very difficult. And they are going for the most difficult way of doing it, which is using electromagnetic confinement and lasers. Now, these are two different forms, but they're extremely difficult to achieve. And another problem, a big problem, is that the current model of the atom, the state of physics, has hit a roadblock because the current model of the atom.
When you say model of atom, I mean, it's something that's there. It's not like we now create a model and now that's the model of the atom.
Okay.
The model of the atom is the model of the atom. I mean,
well,
what
okay.
do you mean
So
by that?
when I say atom, what comes in your mind? How do you think of it? What does it look like?
I would think it is the smallest particle
Yeah,
that
but
can be...
What... that
it could
you
be
can go,
anything.
you could go even further down and break the atom into smaller particles, right? So what does it look like? It looks like the solar system model, right? There's this big
I
thing.
would think, yeah.
There's this big nucleus in the middle, and then there are smaller electrons revolving around it, but in three-dimensional, not flat like the solar system, but in three-dimensional. Well, and what's in the nucleus? How are those particles sitting with each other?
I think they're
that is
always
the
at
model.
the moment, right? It's in a movement. It is always... It is
jiggling?
or like moving. Like it's not still. It's not like...
But
like something
you mean the
that's static.
nucleus?
In the nucleus, but in the atom itself.
Yeah, so the electrons are moving,
but in the nucleus too.
in the nucleus. Okay.
Yeah.
What's in the nucleus? There's protons and neutrons, right? And how are they... What kind of relationship do they have? How are they sitting with each other?
I think they don't like each other.
Okay. So, the protons cannot like each other because like charges repel and unlike charges attract. Okay, so that is the model that I'm talking about. Okay. Because how you understand the atom helps you understand everything else, which is nuclear physics and chemistry, and from there to biology.
Yeah.
So the current model of the atom, which is called the standard model of the atom, is not useful for fusion research. We need a new model of the atom.
So what do you suggest is a new model? Now it's not a little controversial. I think you just went too controversial. You're just saying
huge controversy.
that everything in physics is not what you read is not what the truth is. Now that's a huge controversy.
Yeah. So I'm not saying throw out all of physics or particle physics. So what we need is new players on the marketplace, right? New theories for the atom, new atomic theories, new particle theories. Now, there is one such theory that I'm a big fan of, and that is called the structured model of the atom, SAM, structured atomic model. Okay, SAM. So the standard atomic model is a newer model of the atom, but that would help us explain seemingly anomalous phenomena such as cold fusion, and also open up possibilities to do fusion with heavier elements such as helium and boron and lithium and so on, and even bigger than that, all the way up to iron. So this opens up a huge possibility for the future for clean energy, and this requires a lot more research. So I'll leave it there on that.
Yeah, I mean, that is something we need to touch upon later part of the season, yes, another season. Now that was nuclear fusion and nuclear fission that's happening right now. What currently in most of the nuclear plants what they do, and the future is nuclear fusion with the newer atomic theories.
Yeah,
is it?
And fission will be around. There'll be generation 4 and generation 5 reactors, breeder reactors that reuse nuclear waste as new fuel, and then small modular reactors, SMRs, those will be around, and then nuclear propulsion using fission will be available. And in addition, we'll have fusion.
So that's the future, and we would love to be reaching in a place where we can derive energy from multiple sources. Now, from where we begin in the last episode, part 1 till now, the only answer that I could think of is we need to have different players, different eggs.
Exactly. Different baskets.
And in different baskets.
Yes.
That's the conclusion. Now, coming back to the present, one of the things that I know, Philip, you are very passionate about is deriving energy from waste, because the current situation is the current situation because of the waste. So why shouldn't we go back to the roots and solve problems right there? Then looking at the stars and thinking of we'll mine some lithium
Asteroid. Yeah.
yeah. So let's talk about waste
Yes.
bioenergy.
So we can actually turn waste into a energy source. We can reconsider waste as an energy source and thereby solve our pollution problems.
So when you talk waste, you're talking about all the landfills, all the animal waste, human waste,
Yes.
anything that is waste.
Anything, municipal solid waste, food waste, and
Plastic
electronic waste, plastic waste,
Wow.
medical waste,
Okay.
biological hazardous waste, from hospitals and bioresearch and so on. So anything that has hydrocarbons in them can be turned into energy. And that is using plasma gasification.
This is something that's currently not there.
No.
It's something in theory you think is possible, or is it something people are currently researching on? So what stage are we in? What is plasma gas? I know in the past many episodes we have spoken about, because it's purely because of the passion Philip has towards waste. But to touch upon it in a little bit more open way is to understand, is it currently available? Where are we with this research?
So there are many companies who are producing plasma gasifiers. They tend to be big companies for big projects like municipalities and cities.
Where is that? I have not seen one yet.
So there's several in China. There's a new one in Pune in India, plasma gasifier. And there are several in the US and North America and Europe, and several were shut down for financial reasons as well. But there are also smaller gasifiers on U.S. aircraft carriers, the Nimitz class, and there are plasma gasifiers being sold for cruise ships and other applications as well.
So what I'm deriving out of what you said is it's financially very expensive to have an industrial size gasification, and it's not currently available.
So that's using the current state of the art, which is the plasma torch. And that is currently expensive. And so the economy of scale requires extremely large plants from these big scale manufacturers. But they can be scaled down. The prices have come down because of better manufacturing and better materials that are available. And also we can switch to microwave plasma arc sources. And so microwave plasma gasifiers are much more efficient, can be scaled down cheaper, and scaled up in numbers, unlike the traditional arc gasifiers. So the costs are coming down and will come down, and the advantages are plenty. What this opens up is the possibility that all of our hydrocarbon waste that comes from our homes, the sewage waste, toilet waste, and then the kitchen waste and municipal solid waste, and then all of your plastics and everything can be gasified and turned into syngas. And then once you get syngas, you can liberate the hydrogen for the hydrogen economy, or you can convert syngas into electricity or produce larger fuels such as gasoline or diesel or aviation fuel, or even plastics. So the possibilities are just endless, and this technology can transform the way we build cities and way we manage waste and the way we handle sewage and so on. So it's just tremendously amazing technology with lots of possibilities.
So where are we now, and how far are we to reach that place where it is available, municipalities, cities, countries, to use it at that scale?
So there's a lot of research being done, and there is manufacturing also happening. Small-scale microwave plasma gasification is already available. We're talking about 10 kilowatt size. So these can be scaled up in size and in numbers. And better, more efficient, effective plasma torches are now available. DC, AC, and RF radio frequency type plasma torches. And we have better materials. And so there's more adoption of this technology at smaller scales, like we were saying, 100 kilowatts to 1 megawatt size. And we need to see much more development.
Just when you said that, I just got a question in my mind. With the current technology that's available with microwave plasma gasification. In a household like yours, which is small household, you just have your energy needs in the kitchen, in air conditioning, electricity. Can one think of using it as part of the grid?
Yes. So that's the advantage of microwave plasma gasification, that you can scale it down, just like you have a microwave oven in your home, which is typically rated at about 1 kilowatts of power rating. You can have a microwave plasma waste to electricity converter that takes the place of the generators or diesel generators that people have in their homes.
That's amazing.
And so you could turn all your waste from your kitchen, from your homes, and then even your toilet waste can be processed and turned into energy and reused in the home as electricity, or it can be processed for other applications as well.
That's an amazing news, especially for developing countries where energy, they rely on generators and things like that because the power is not reliable. This can be the way forward. And also it answers the need of the hour with regards to waste management. That sounds great.
Yeah, because you don't have to transport all those waste, into a landfill or to a collection center. It can be processed at close to the site where it's being generated.
That really is such great news, especially when for a single problem we have so many solutions. That's a great place to be in. So this is what we represent, right, Philip? I mean, I know if Vibha was here, she would have agreed that, if you start only looking at problems, you'll only see problems. But when you start exploring the solution and you start bringing into light the people, the things that people are doing, human ingenuity, like you say, there are so many people in search of solutions and bringing forth solutions, and there are solutions that are worked on. This is a great place to wrap up our sustainable energy episode, which was supposed to be one episode, and it now turned out to be in 2 parts because it was really, the solutions are so many.
Yeah, and we're not even done talking, so I guess we should have more episodes in the coming season.
We will. In the coming seasons, we will be picking up each sustainable solutions individually and exploring it. So we can spend more time on each solutions. So we can safely say that renewable energy is the future. The only difference is we cannot rely on a single source of energy. It needs to be multiple. It needs to be individualized. It needs to be created. So every society would have a different mix of energy depending on what's available to them, what their landscape is, what the people's need are.
And waste will become a source of energy.
I can't wait for that to happen. I mean, think about those, when you create those models for future cities and you see this beautiful, clean, green cities.
Yeah.
And that can very well be possible.
Yes.
That is amazing. Can't wait for that. With this, we come to the end of the episode. Thank you so much for listening in. Me and Philip, we had so much fun talking about it, and we really, really miss Vibha.
And we hope to hear from all of you listeners.
Yes, please
with questions and comments and anything else.
Do remember to follow us, subscribe to our channels, and see you all in the next episode.
Bye, everybody.
Thank you so much, everyone. Take care. Bye.